Okay, thank you. So I'm going to talk briefly because, 40 minutes is not enough to talk a lot about the WRF Chem model. And just to give you a taste of the model, like the recent applications of the model in some interesting air quality applications. And also Doug Lowe will present some applications of the WRF Chem model. So as you know, this model, WRF Chem, is a community model, and many people from the US, also from Mexico, many other countries, Europe, Asia, contributed, made significant contributions to the development of this model. So where we are with the WRF Chem model. And some facts, first of all, WRF Chem model is a fully coupled metrology chemistry model. So you can run both metrology and chemistry simultaneously. The current version of WRF Chem, which is 4.1.3, contains multiple parameterizations to simulate greenhouse gases. You can simulate CO2, methane, if you have emissions, N2O, etc. Dust, fires, volcanoes, and gas and aerosol chemistry, including ozone chemistry, and SOA, and so on. And we have multiple chemistry schemes with different levels of complexity, photolysis, removal processes, and also, as I said, you can do chemistry metrology interactions. You can simulate that explicitly by WRF Chem. So many collaborators I mentioned already, and there are about 3,000, probably now even more users. They have registered, they are WRF users, but their main interest is the chemistry. And this is a web page, and it's being updated. And also we have this like discussions email list. If you have something interesting to share with the user community, feel free to send email. So what's specific about WRF Chem? As I said, the chemistry is online and it's completely embedded within the WRF code infrastructure. So you maintain one single modeling software package. It's WRF with chemistry. And the chemistry and metrology, they share the same vertical and horizontal grid, so you don't need to do any special interpolation or temporal interpolation because the advection is done by the same WRF advection scheme. And for subgrid scale transport, for example, for turbulent mixing, they use the same boundary layer schemes or convection, deep convection schemes. And as I said, you don't need to do interpolation, you don't need to run WRF model and then run another model. So in terms of data management, it's quite easy to handle. So many applications, and you will see some examples. So what do we need to run for such a modeling system? First of all, advection and diffusion, again, is all done by WRF. But then schemes or parameterizations which can handle these different processes, such as, for example, biogenic emissions, or fires, sea salt, dust, and also removal processes. Also, we have, for example, aqueous phase chemistry in WRF Chem. So I move a little fast again because of the tight schedule. So some of you are familiar with the gas chemistry schemes, and in WRF Chem, this is a list of the gas chemistry schemes which can simulate ozone, radicals, and other species. And you can see this list ranging from radon, Rackham, carbon bond mechanisms, Mozart, and CRIMEC, which is quite advanced scheme Doug will talk about. And these schemes are coupled to many different aerosol schemes, and also aqueous chemistry schemes, which can be applied for different applications ranging from the regional, very high resolution air quality to very large scale, let's say, atmospheric chemistry simulations. So in recent years, the community, our collaborators, we made some updates, significant updates in the WRF Chem model. Here is a list. I just want to mention a few. For example, stratospheric ozone, because if you have, especially in high altitudes, you can get these stratospheric intrusion events. For that, you need to parameterize. You need these upper boundary conditions, which is hard to estimate, or you have to use other models. So this is a simple parameterization, and then updates to the gas chemistry scheme. And this is aerosol, this is gas chemistry scheme, and then, for example, this new isopropyl aerosol thermodynamics model, and for solubility, also very useful diagnostic tools such as integrated reaction rate diagnostic options that developed by NCAR. So now applications. So I decided to show you applications which probably of interest to you, because Mexico also has quite developed oil and gas industry. About the last 2 decades in the US, there have been huge development in the shale oil and gas drilling. These are shale basins in the US. And what happened is in 2005 and 2008 in Wyoming, during winter, quite high ozone concentrations were observed near these oil and gas sites. And then in 2013, so this may be hard to believe, within the entire year, the highest concentrations didn't actually take place in Los Angeles. It happened in Uinta Basin, where maybe, I don't know, a few thousand people live, but there's a lot of oil and gas production. So NOAA, EPA, and others did a lot of studies there, and this is one of the like ground-based measurements. Ozone reaching, this is ppb 120. Again, you can see this is January, February, when there is snow on the ground and sub-freezing temperatures. So there's another kind of highlight here is with bottom-up EPA emissions, we were not able to get ozone. Also, we had to do some changes in the model. I can talk offline if you're interested. But again, with the same improved model, we couldn't get oil and gas ozone for these episodes. And when we use our top-down emissions, which are based on the atmospheric measurements, but then we infer by using methane, VOC, and NOx emissions, we can get these daytime very high ozone values. And this is one of the significant applications of the WRF Chem model. And also, not many models, I mean, it's very hard for air quality models to get these ozone events when boundary layers are about 100 meters deep. Okay, another application in 2010, excuse me, in Gulf of Mexico, one of these oil platforms belonging to BP exploded, deep water horizon well, and it caused huge oil spill. Probably you remember. And actually it happens that we were lucky that NOAA aircraft was doing measurements in California, studying air quality, and they were able to fly to the Gulf of Mexico. They did measurements, and what they found is very high levels. This is ppb of aromatic species. And Lynn Russell, she talked about the VOCs, their contribution to secondary organic aerosols. Of course, they measured high organic aerosols. By using WRF Chem, we also did some modifications in the chemistry, but by taking advantage of this flexible modeling framework, so-called KPP tool, and also taking advantage of the measurements, and there have been many great talks today about the measurements, very detailed measurements, VOC, NOx, etc. We were able to estimate the emissions from this oil spill, because of course the inventors don't have something like this, and we were able to estimate these high second organic aerosols by using WRF Chem model, and it was published in this paper. So another example is fires. It has been one of huge, probably the major air pollution source in the US during summers. And what is also happening last several years, new satellites in the US have been launched. And you can see this is a JPSS-1 satellite. There are actually 2 JPSS satellites in the afternoon, the orbit. And now you will see there are, these are like kind of similar orbits, like modest, but due to the wide scan angles, they don't have any gaps. So every day you get this global coverage. And there are 2 of these satellites, 2 modest, and also there are geostation satellites. So we can take the fire radiative power data. It's like an indicator of fire intensity or fire heat flux, and ingest into the WRF Chem model. And we have 2 domains. These are fully operational models. And these names might be confusing. This means rapid refresh. This means high resolution rapid refresh, which is running at 3 kilometer resolution for the entire this US lower 48 states, and also part of Mexico. These names, just because they are based on some data estimation systems. How the bottom line here is, all these models are based on the WRF and WRF Chem models. So in last spring, actually Mexico had many wildfires, also probably some prescribed burns. And Augustine Garcia, we had good some communication about this, and you were looking at this, and it was very interesting actually to see these so many fires in Mexico. I believe Mexico City also was affected. I think somebody shows this. So my point here is now by taking advantage of the WRF Chem model, a single tracer here because it's expensive to do chemistry resolution. And by using this WRF Chem structure, basically simulating feedback, now we can forecast smoke in high spatial resolution. It helped people, can you run this, click on that, yeah. It helped our forecasters in California. There was this campfire, which is the most devastating, yeah, click on that please, yeah. Devastating fire in California's history. About 100 people died. This happened last November, in 2018 November. And what you see here, actually, the plumes from the model, and again, WRF Chem model, and those circles actually show the concentrations. And you see this complex transport. Like here, it's clear, but then on these both sides, actually, the concentrations are significantly were high, and San Francisco, the Bay Area, was badly affected. Like about 2 weeks, they had almost about 100 micrograms of PM every day. And also the purple sensors, I think you showed this network was one of the emerging data sets in the US, air quality sensors. So the bottom line here is, again, this high resolution model, a coupled model, WRF Chem, by taking advantage of the satellite data, we can simulate this smoke transport over this complex terrain quite well. Now, there are other applications. For example, our colleagues at NCAR, they developed these nice diagnostic tools to look at different things like trajectories and like model output along trajectories and so on. So feel free to contact me if you have questions. And these tools are already in the official community version of the WRF Chem model. And then our collaborators, for example, in Middle East, they are using WRF Chem. Actually, many people are using WRF Chem for dust forecasting. And this group, they have published a number of papers where they improved this dust forecasting by using WRF Chem and also the land use data which goes into WRF Chem for dust emissions, dust emission parameterization. Excuse me. And okay. And another application I believe also of interest to Mexico and other countries is volcanoes. For volcanic ash, WRF Chem has that parameterization, and this was a well-known volcano in Iceland in 2012, which shut down the airspace for quite like several days at least, and the colleagues in Austria, they're using WRF Chem to simulate the effects of this volcanic ash on air quality and also on weather. And another interesting application which I learned recently is that actually in 2018 in New Delhi, in collaboration with NCAR, they launched fully operational WRF Chem system for air quality forecasting. And what's interesting is they have full coupling. So if there's a significant smoke, which like happened in Mexico City, the previous speaker showed that case. So it affects the temperature, radiation. The model can forecast that. Also, it includes this data assimilation system. Arthur will talk about that. So it is now running. They have a web page you can check. And also another interesting application, there's WRF Chem coupling. This is actually already published with an ocean model where they look at these different, processes, and it's an interesting application. I thought probably some of you might find useful. And the next, I want to invite Doug from University of Manchester. So
yes.
You can continue and please, yeah.
Okay. Thank you, Ravan. So yes, so I work at the University of Manchester in the UK, and I would like to talk a little bit about some of the developments in WRF Chem, which has been going on in the UK and in Ireland. So, as Ravan mentioned earlier, there's quite a wide range of chemical mechanisms inside of WRF Chem. The most complex in there at the moment in the release model is CRIMEC. Now, CRIMEC is based on the MCM master chemical mechanism, which is aimed at trying to model ozone production. So it's a very detailed volatile organic compound and NOx model, and it gets focuses on this oxidation cycle with reactions with NOx and to produce ozone. Now, there's many thousands of VOCs identified in the atmosphere. The MCM is one of the most explicit representations of this scheme. The version 3.1, which this is a little bit old, this is what the current CRIMEC scheme is based on, had over 4,000 species and over 12,000 reactions. Now, this was all kind of calculated, put together by hand. Nowadays, we've got the gecko mechanism, which is used for automating building these schemes. But because as you go up in the number of carbon atoms in your VOCs, the number of possible isomers for those molecules increases exponentially. So nowadays, we can't actually calculate these by hand. We have to have automated systems to try and build these schemes. But this is aimed at ozone chemistry, and so we can get the chemistry running quite well for that with this scheme. There's a website here which describes this scheme in detail. Now, this is a little bit too complex to go into WRF Chem for large-scale model runs. So what we did was that we took the common representative intermediates mechanism. So the idea behind the design of this was that you would lump oxidation products based on the number of carbon-to-carbon bonds and the carbon-to-hydrogen bonds, so that you can reduce the complexity of the scheme while still preserving the ozone production potential of that scheme. So the base CRIMEC scheme went down to 434 species. We got further reductions of complexity by lumping the emitted VOCs. So the CRIMEC scheme inside of WRF Chem now is only 196 species, which is still the most complex chemical scheme there, but very reduced from the MCM, and 555 reactions. So that's what we have in WRF Chem at the moment. In the UK, there's a lot of development still going on for the MCM and also for CRIMEC. So there's now the CRIMEC version 2.2 mechanism, which we'll be looking to try and put in at a future date. And also there's lots of development going on, getting the reaction rates more refined, making sure the chemistry is as good as it can be. So just to say, so I won't go into too much detail on the research work we've been doing with WRF Chem at Manchester. One thing I will do is a quick plug for a forecast website that we have, which this is for a teaching tool, so we don't do a lot of data assimilation after we produce the forecast that serious forecasts do, but we run daily forecasts, and we have an archive on that website going back in, slightly patchy on some dates, but going back about 4 or 5 years of both meteorological and air quality modeling forecasts. And this is run with the CRIMEC mechanism and the 8-bin mosaic aerosol model at a 12 by 12 kilometer resolution. And there's more information on the website for that. So over in Ireland at the University of Galway, Colin O'Dowd's group have just started running air quality forecast using CRIMEC and mosaic again as well. But they're doing a little bit more development on how to deal with emissions which are more poorly represented in the standard emission data sets. So they've been looking at these pollution events here. We've got some AMS data here. These pink periods are when we have cold snaps, and this is warmer periods. So you can see that we have quite these large spikes in organic particulates during these cold snaps. So what they've done at Galway is they've added an emission factor which is related to the household density in Dublin, and from that you get the release of particulate matter, assuming 10 kilograms of fuel burnt per house per night on these cold snaps. And this is connected to the temperature within the model. You're getting a temperature-dependent enhancement factor with this diurnal cycle here. So here is an example of some analysis they did. So this black line down here is the model forecast with the standard emission data set without this factor added in. And the red line is the measurement data. So you can see that standard emission data sets are completely missing these events. Once you add in this temperature-dependent emission factor for the model, this green line, blue line possibly, you're getting a lot more of these emission events here. We're not quite getting the magnitude of this one, but we are a lot closer. So they're doing a lot of experiment with this to look at what these, how to deal with these irregular events. So at the University of Birmingham, they're working with, so WRF doesn't just do large scale. You can also run it in large eddy simulations scale. So you will be running, this is running at a 20-meter resolution, grid resolution, running over an area, I think it's around about 3 kilometers by 3 kilometers. And so what they've been trying to look at is the evolution in the distribution of organic aerosol, semi-volatile organic aerosols. So this is an area of central London, and you've got Marylebone here, and you have quite a lot of heavy traffic on these roads. So they're looking above canopy at the particulates from here, and you can see as you move away, so this is the total ultrafine particle number concentration, and as you move away from the road, you can see it dropping away. So they've got 2 measurement sites at Marylebone and then slightly further away, and you're looking here at this distribution. So this is size, particle size and particle number, and you can see how as you move away, so this is at Marylebone, and then this is further away from, I guess, it's about 200 meters away. You can see a reduction in the peak of the total number, and you can see a shift in the particle size as you get evaporation and dispersion effects. And then here as well, because they have been looking at a range of molecular sizes, and so this is a range of volatility, you can see the change in the volatility profile of your organic aerosol. And this is the reference for a paper which was published at the end of last year, and a few details on the model. So they're using, to the LES model, they added their own aerosol scheme, which has got 15 size bins and 17 surrogate alkene components, so about 300 traces. So very expensive. They ran the chemistry part of this simulation for about 30 minutes model time because it's so expensive. So at the other scale of aerosol modeling in WRF Chem, you can work with the go-kart scheme, which is a bulk aerosol scheme, which is used for dust modeling in a lot of applications. What Professor Carsten Skov at the University of Worcester has done is he's adapted this scheme to look at pollen modeling. So he's adapted the go-kart aerosol, added habitat maps and plant density information to the land use categories which go into the model. And you can then have this coupling, so you generate these bioaerosols going into the dispersion model. Because it's coupled to go-kart, you can have your radiative impacts, feedbacks added into that. And so he's been looking at how those impact your forecasts of pollen distribution. So here's a couple, and this is very preliminary work. So he's still doing a lot of analysis on trying to understand what these results mean. So this is, the red line here are observations of pollen counts, daily mean concentration in grains per cubic meter. So Worcester is kind of the rural heartland of the UK. The Isle of Wight is on the coast, southern coast, next to the English Channel. So the red lines here are measurements going through from March through to April, and the same here. And so inland you can get a lot of the features of the release of pollen. As you add in the feedbacks, radiative feedbacks, you get quite a change in the loading of these pollen counts. He's still looking into why that is like that. Yes. So, have I? You've moved slides. This is slightly different too. I'll hand back to Ravan now.
Yeah, so I wanted to just have these few concluding remarks. First of all, if you want to start with WRF Chem, or you want to learn about the recent applications, new developments, we suggest you to check the WRF Chem references, and it's on the web page. And also, as I said, we have a new email list for the discussions, and we strongly recommend all the users signing up to the WRF Chem list, because sometimes also important bug fixes are posted there. And we have user guides actually, and many tutorial presentations. But please note that because of our limited resources, it's not very well, detailed and very well organized. Unfortunately, because it's so big model, you have already, I think, you have realized it's hard to just describe every component or each component of this big modeling system. And here are some links, and then the email address you can contact the WRF Chem team at NOAA. And also, I thought we are talking about the model current status, but also just briefly, I want to talk about the future. So where are we going from here? We have these great models, CMAC, WRF Chem, other models. But however, there's a need, which has been realized quite some time ago, is to develop unified modeling systems for the global and regional applications, also with these non-uniform grids. where you can zoom over the regions of the interest. And NOAA and NCAR are working on similar kind of modeling systems. And the idea is at some point you can choose different dynamical cores, different advection schemes with different chemistry schemes. So they are all these interoperable. So this is the future, but it's actually the process has started. And this also is related to the question Arthur had about these global boundary conditions. Because what happens, we are doing now, we are using a different model or different models on a global scale, and then completely different modeling tools on a regional scale. So the idea is to unify them and also to take advantage of these non-uniform grids. Yeah, thank you, and we are happy to take questions.
¿Preguntas?
We will be around, so you...
Yeah. Cover too many topics.
¿Preguntas? I work here. My name is Aaron Hasilevich. I am a little bit interested in, we have a model to predict pollen here in our center. Yes. And of course, it's not a model with WRF, but I was puzzled by the aerodynamics that might be used to be able to produce the transport of pollen. Do you have any information about that?
I have to apologize, I don't. I mean, it's for go-kart aerosol model, so for go-kart, there is an assumed size distribution, I believe, for the aerosol. I could put you in contact with Carsten so that you could ask questions on that, and he'll be able to answer that. Okay.
I just want to add that you can also use more advanced schemes with size distribution to do the pollen modeling. So, but since we are interested in mass, usually, for pollen, they use go-kart, I guess.
What I'm concerned is in the aerodynamics, because pollen has very, very complex.
Yeah. I see. Yeah.
So,
no, I'm sure he'll be very happy to speak to you about.
¿Alguna otra pregunta? Well, just regarding the application for the high resolution, for the city, do you know if they modified the WRF Chem as in WRF-Fire? Because I don't know if WRF itself can handle that level of resolution. I mean, the order of meters.
So it's the system itself. It's for WRF large eddy simulation model. So that can cope. So that model itself copes with that scale. Oh. Now, they added in their extra aerosol scheme, so I don't think WRF Chem is fully connected to the LES. Okay. So they put in their own aerosol scheme for that work.
Okay. Also, I'm interested in the high-resolution applications of WRF, as you mentioned, 20 meters.
Yes.
We are starting here a group with CFD, at CFD level, and we would like to connect it to WRF, to have to connect WRF and CFD.
Yes.
For your application of WRF, do you consider different parameterizations, especially of turbulence? And if you include, how do you include urban morphology?
So, yes, when I was asking them about this work, they said explicitly that they're not dealing with street canyons. So what they were just looking above the urban canopy. So I think there is a bit of roughness in there in that surface to give you the effect on your winds, but you're not actually, the model grid doesn't adjust over that.
So I'd like to expand on his answer.
Okay.
There's a couple groups at NCAR that are looking at the junction of a CFD model and WRF. So if you were to contact RAL, the Research Applications Laboratory, that would be one mechanism. And then M-Cubed, the large-scale eddy modeling group, also simulation group, also would be helpful.
Can I add? About your question, also another example. Actually, there is WRF at NCAR. There is a team which they are running WRF with four fires at 30-meter resolution, where they have complex terrain because they look at fire spread in valleys, over hills, etc. So you can run. The challenge is the chemistry, which you can run, but it's computation expensive. But you can do like traces. So yeah, you can run WRF for this like urban, this like heterogeneous terrain.
¿Alguna otra pregunta? Thank you very much for your presentation. Thank you very much.